You step out onto the platform, tentatively at first. It was platform 9, right? That would be awkward. A train whistle blares out in the distance and you realise that you're late. Hurriedly you pile your belongings onto a cart and you spin it round to face the barrier. You take a moment to shake off that last remaining bit of self-doubt and you sprint with all your might towards the barrier. You wake up a moment later in a pool of blood and social embarrassment. You're not a quantum mechanical object, Harry. A glimmer of truth actually teases through this situation if, instead of considering yourself fueled maybe by one too many butterbeers, you consider an electron heading towards that barrier. Because even though electrons have mass and they have charge and they have these properties that we think we understand, they obey the universal speed limit and they reasonably reliably travel down some tubes to power our internets, it turns out if you direct that electron towards a barrier, there is a chance that it will appear on the other side of that barrier having never passed through the barrier itself. Accio electron. This phenomenon is called quantum tunneling, and it is a property of quantum mechanics and maybe the best example of how counterintuitive and strange the quantum world can be. It arrives, however, from an idea that we have talked about before, the idea that there is a wavelength associated with everything. Do you have mass and velocity? Well, then you have momentum, and de Broglie says that you have a wavelength associated with that momentum that arises due to the uncertainty in your position. That's right, I am a wave. You are a wave. Your grandmother is a wave. Saucy. Unfortunately, gone are the days where we're only worried that light exhibits this weird particle waviness, because it turns out that everything does. So why then, do you ask, did I not make it through the barrier? Why am I not currently sitting in potions class with Professor Gandalf? Well, because you are quite massive. Sorry. Your wavelength is there, but it is so small that it doesn't really merit worth thinking about. For particles, however, this isn't the case. Their wave-like properties are very significant. This is why when we think about atoms, we consider the electrons that surround them as a sort of fuzz or smudge or sea of oscillations, because electrons have a certain undeterminable location. They are a wave oscillating about the nucleus, and this waviness is what allows them to tunnel. Okay, so let's imagine again. Let's imagine that you have a pet electron. Each night you put him to bed in a box and he happily wobbles around inside, described by this wave function, which basically tells us where he likes to hang out the most. This wave function maps out his positional likelihood, but where he is any more specifically than this, we can't really say. The same way you can't really point to exactly where a wave is on the water. This is his waviness quantified. Most of the time he enjoys hanging out in the middle of the box, but sometimes he does deviate off to the side. And if we look closely at his wave function, although we notice that it is exponentially attenuated by the walls of the box, it does actually extend beyond them. He can escape not by digging through, but simply because he can exist at 1 second inside the box and another second outside the box, without any necessity in having a position at every point in between. So what I'm saying is that you can wake up one morning to the shrill tones of your mother, who is exclaiming that your electron has got in the rubbish bins again. What's even more interesting is that what we have described here, although somewhat simplified, is exactly how an atom works. Place a proton at the center of the box and remove the walls, and the electron will remain confined in this area, attracted by the charge of the proton. So we say that opposite charges attract, but why is it that the electron and the proton don't just stick side by side? Well, we've said that this is because the electron's position doesn't really behave like this, it behaves like a wave. And asking this question doesn't make any more sense than saying, okay, please stick this wave on the water to this beach ball. I did it, Mom! But here he is, anyway, my first hydrogen atom. And if we go one step further, and if we take 2 of these hydrogen atoms, and we bombard them together, we smash them together so that they get very, very, very close, even though those protons are vigorously resisting coming into contact with each other due to their charge, we can push them so close together that their wave functions actually overlap, and they blink into existence as a new atom. And it turns out that this is how the sun works. What was I supposed to be explaining? Where am I? Science, eh? Yucky. So how do we actually know that this sort of quantum befuddlery is actually real in any way? Why do we care? Is it something we can actually interact with and understand and see, or is it just hidden away in the mathematics and completely inconsequential to our lives? Well, it turns out what I'm actually trying to do with my system at the moment involves a little bit of quantum mechanics in sort of a roundabout way, but let's take a look at it and see if it sort of illuminates the situation and puts a real physical example sort of under the microscope, if you will. I'm building a microscope. That's the pun. So what I'm trying to do at the moment to my system is basically add something called TIRF imaging, which is total internal reflection fluorescence imaging. Total internal reflection is an idea which you probably already know about, even if you don't think you do, which is the idea that if you look at a transparent surface under quite a hard angle, you won't see what's on the other side of the transparent surface, you'll see what is sort of at the complementary angle to yourself. Because any light coming from those sharp angles basically is reflected rather than transmitted. Hence, total internal reflection. And what I'm trying to do is basically set this sort of scenario up inside the illumination objective. Now the illumination objective is basically just a really, really powerful lens. But all I'm basically trying to do is pass some light into it in such a way that it reflects off the top surface of it and exits back through the entrance. So effectively what I set up is that no light actually passes through the objective, right? Right, and I can see this by measuring the power going in and the power coming out, and I notice that they're perfectly equal to each other. However, say if I were to put a bead or something very small just above the top of the objective, suddenly I would see a power drop. Because although that light is forbidden to pass through that gap because it's totally internally reflecting, what it can still do is quantum tunnel its way to scatter off of that bead. So now I won't have an equal amount of light going in as light coming out because some of it is just being scattered. And it turns out that you can measure the light intensity going in compared to how much is coming out to such sensitivity that it becomes a really interesting technique, particularly to someone like me who is often trying to track things like nanoparticles. And the logical extension of this technique is that if you use it with fluorescent particles, and say you shine in green light, if a fluorescing particle gets in your focus, then that green light quantum tunnels its way over to it, interacts with it, and you see that power drop, but also you suddenly see some, say, red light return to you as that fluorophore emits some fluorescent light. So basically you've effectively got this sort of two-step verification as to are you seeing something in your focus, and is it the particle of interest that you actually want to see? Does it fluoresce at the right color? And this is why it's such an interesting technique to us. Quantum tunneling made personable, you're welcome. Anyway, I just thought I'd make this a little bit more hands-on-y, something you can actually sort of have a physical representation or an example of, that it does in fact happen in the real world and isn't just in the private, where am I going with that? In the private world of mathematical books and boring bits. I hope you enjoyed this. If you're interested in keeping up to date with my videos, then please subscribe to my channel. Until then, I will see you next week. Bye 5.